So this time we're taking a look at section 12.3. And section 12.3 deals with the dot product. Now, we're going to start with the definition. We're going to let A be a vector in three-dimensional space. And it'll have components A1, A2, and A3. And we're going to let B also be a vector in three-dimensional space, and its components will be B1, B2, and B3. Then dot product of A and B, which is denoted by A dot B. It's a number, and the way you get this number is you take corresponding components of A and B, multiply them together, and then add those products that you get. So what that means is that we'll take A1 times B1, that'll give us a first product, and we'll take A2 times B2, which is the second product, and it gets added to the first. And then we'll take A3 times B3, and that gets added to A1 B1 plus A2 B2. And so this is our dot product of A and B. And you can also do this for vectors in two-dimensional space. So if you have A with components A1 and A2, and B with components B1 and B2, then the dot product of A and B is A1 B1 plus A2 and B2. Now we're going to see a number of instances in which this dot product is going to come into play. So let's take a look at some properties of the dot product. So we're going to let A, B, and C be vectors in V3. And we're also going to let C be a scalar. So we have this vector C that has the arrow notation, but we have the scalar C that does not. And so that's how we know the difference between the two. The first property that we have is that if we take A dotted with A, that's the same thing as the square of the magnitude of A. And we can see this without too much difficulty. If you take A dot A, A has components A1, A2, and A3. And so we dot this vector with itself, multiply the first components together, that'll give us an A1 squared. Multiply the second components together, gives us A2 squared, and that's added to what we had before. You multiply the third components together, you get an A3 squared, and that's added to what we had before as well. Well, this is the sum of the squares of the components of A. We know the magnitude is the square root of the sum of the squares of the components of A. This doesn't have the square root, and so it turns out that this is the same thing as the square of the magnitude of A. Second property is that if we take A dot B That's the same thing as b dot a. Now we can see this without too much difficulty as well, because we take a dot b, we have this vector of components a1, a2, and a3 dotted with the vector of components b1, b2, and b3. And according to the definition of the dot product, this is a1, b1 plus a2, b2 plus a3, b3. But what we have to keep in mind is that the components of A and the components of B are real numbers. And one thing that's really nice about multiplying real numbers together is that the order doesn't matter. That is, A1 times B1 is equivalent to B1 times A1. A2 B2 is the same as B2 A2. And A3 B3 is the same thing as B3 A3. So if we can switch the order of the factors in each one of these products, but if you were to do that, notice that it's the B components that are showing up first in each of these products, and the A component is showing up second. And so you can write this as following. And this is the same thing as B dotted with A. No, I don't plan to prove every single one of these properties that we're about to see, but this just gives you an indication as to why the first couple work out the way they do. The third property we have is A dotted with B plus C is equal to A dot B plus A dot C. So we have this nice distributive property here with the dot product. Fourth property that we have is CA, and this is the scalar C now. CA dotted with B is equal to scalar C times A dot B, which is equal to A dotted with CB. So all three of those are equal to each other. And what this is telling us is that we have a bit of flexibility as to when we do the scalar multiplication. That is, we could multiply A by the scalar first, and that gives us a vector which we can then dot with B. Or we could take the dot product of A and B first, multiply that number by C. Or we could multiply the vector B by a scalar, and then take A dotted with that vector. And then with number 5, if we dot the 0 vector with A, we get 0. Now, something that is, I think, worth mentioning here is that when we take a look at this 0 dot A is equal to 0, this is the 0 vector, while this is the scalar 0. Remember, your dot product is supposed to give you a number. So when we take the dot product of two vectors, once again, we're getting a number. So the vector notation is certainly appropriate here, not so much on the right side of the equation. All right, so let's take a look at this theorem. All right, so in this theorem, we have if theta is the angle between the vectors A and B, then A dot B is the magnitude of A times the magnitude of B times the cosine of theta. And so what I'd like to do here is give some sort of reasoning behind why this works out the way it does. And so we'll start out with a diagram where we have vectors A and B, and we'll have A along here, B along here, and we'll have this angle theta that's between those two vectors. Now, you might notice that this collection of vectors forms two sides of a triangle that we can finish off when we take a look at throwing this vector in. Now notice that the vector A is actually the sum of this vector and that vector, because the initial point of this vector is at the terminal point of B. So we know that this vector has a representation of A minus B because B plus A minus B is equal to A. But we can go back to a pretty familiar formula. You see, if I set up a triangle like so, that looks pretty much like the one we have here, you may remember that there is a formula from Prekaut-Wittrig called the law of cosines. And the law of cosines states that c squared, this is going to be little c squared, equals a squared plus b squared minus 2ab cosine of capital C. So this capital C angle is across from the side with length little c. But that's our law of cosines. And so we think about, well, how does that relate to the triangle as labeled over here? And it turns out that theta is going to be the same thing as, or be analogous to angle C here. But we also have that little a would correspond to the magnitude of A here, little b would correspond to the magnitude of B here, and little c would correspond to the magnitude of A minus B. And so if we think about that, we'll notice that we get the square of the magnitude of A minus B is equal to the square of the magnitude of A plus the square of the magnitude of B minus 2 magnitude of A, magnitude of B, times cosine theta. Now, this is how we at least introduce the cosine of theta. In fact, we have, notice, a negative 2 times magnitude A times magnitude of B times cosine theta. So at least this part is looking a bit like what we see here, but the question then becomes, well, how exactly is it that we introduce the dot product? Because if we're trying to show that this equation is true, we need to incorporate the dot product of A and B somehow. And so one way to think about this is to consider the square of the square of the magnitude of A minus B in a different way. You know, sometimes if you represent the same thing mathematically in two different ways, you can get some nice information out of that. So also, we know that the square of the magnitude of A minus B, well, going back to property 1 here, square of the magnitude of a vector is the dot product of that vector with itself. So we can think of this as a minus b dotted with a minus b. Now, you might say that we don't really have a mechanism by which we can evaluate this a minus b dotted with a minus b, but it actually turns out that we do. And basically it's by clever use of property 3 that we could actually show that a FOIL method type approach would actually work here. And so it turns out that if we expand this out, take a look at the first product, you'll have a dotted with a. So outside product, we would have a dotted with negative b. However, you could say, well, if I have a dotted with negative b, that would be the same as a dotted with negative 1b. So using this part of property 4, we could say, well, that's the same thing as negative 1 times a dot b, or a negative a dot b. Inside product, we would have negative b dotted with a, but commutative property also works, property number 2. So we could say that that's also negative a dot b. And then the last product, negative b dotted with negative b, you could think of that as a positive b dot b. Now, this means that the square of the magnitude of a minus b, well, can be rewritten because you know that a dot a is the same thing as the square of the magnitude of a. Take these two together, we have negative 2 times a dot b. And then your b dot b is the same thing as the square of the magnitude of b. So we now have two different representations for the square of the magnitude of a minus b. We have this representation right there. We have this representation right there. Okay, so both of these representations are representations of the square of the magnitude of a minus b. So those expressions must be equal to each other. Now what this tells us is that the square of the magnitude of a minus 2 times dot product of a and b plus the square of the magnitude of b, well, that's this part here, right, is equal to this expression. So it's equal to square of the magnitude of a plus square of the magnitude of b minus 2 magnitude a magnitude of b cosine theta. So let's write this a little bit more condensed. So once again, there we go. Well, notice that you have square of the magnitude of a as a term on each side of the equation, square of the magnitude of b as a term on each side of the equation. So those are going to cancel out. And what you're left with is a negative 2 times A dot B is equal to negative 2 times magnitude of A times magnitude of B times cosine theta. And so, if we divide both sides of this equation by negative 2, then we got that A dot B is magnitude of A times magnitude of B times cosine theta, which is exactly the result that we see right here. Now, there's also a corollary to this theorem. And it says if theta is the angle between two non-zero vectors A and B, then the cosine of theta is equal to A dot B over magnitude of A times magnitude of B. Now, this is actually pretty easy to get. If you go back to this formula, if you know that A and B are both non-zero vectors, then you know their magnitudes are going to be positive. And so we can divide both sides of this equation by both magnitude of A and magnitude of B. And it works out pretty well for us. All right, so let's take a look at an example. So in this case, we'll find the angle between the vectors A and B, where A has components 2, 2, and negative 1. And B has components 5, negative 3, and 2. Well, to find the angle between those vectors, we need to know something about the dot product of A and B, and we also need to know something about the magnitudes of these two vectors. Now, when we take A dot B, we'll have a 2 times 5 plus 2 times negative 3 plus negative 1 times 2. Well, your 2 times 5 gives you 10. 2 times negative 3 gives you negative 6. Negative 1 times 2 gives you negative 2. And then 10 minus 6 is 4. 4 minus 2 gives you 2. Which means that A dot B is equal to 2. Now when we go to figure out theta, cosine theta, A dot B over magnitude of A times magnitude of B, and this top part we know now would be 2. Now we'll also need to figure out magnitude of A. Now remember, the magnitude of the vector is the square root of the sum of the squares of its components. So magnitude of A will have a 2 squared plus 2 squared plus the square of negative 1 all underneath the radical. So that's the square root of 4 plus 1. And that's square root of 9, or 3. So magnitude of A is 3. Magnitude of B also needs to be figured out. But again, this is square root of the sum of the squares of the components, and 5, negative 3, and 2 are the components of B. So we have the square root of 5 squared plus the square of negative 3 plus 2 squared. And underneath the radical, that'll give us a 25 plus 9 plus 4. And if you add 25, 9, and 4, you get 38. So magnitude of B is the square root of 38. Okay. So once again, cosine theta, A dot B, or magnitude of A times magnitude of B. That's the same formula we saw here in the corollary. But now we know that A dot B is equal to 2. We know the magnitude of A is 3. We know the magnitude of B is the square root of 38. Okay, so this gives us a representation for the cosine of theta. But if you want theta, then you'd want the inverse cosine of 2 over 3 root 38. And this would be a pretty good thing for your calculator to figure out. Make sure that if you want radians, that you're in radian mode. If you want degrees, make sure you're in degree mode. But in degrees, you would have theta as approximately 84 degrees. All right, so let's take a look at some more definitions. So here we have two non-zero vectors. A and B. We say these are orthogonal or perpendicular. If the angle between them is pi over 2. And of course, this pi over 2 is in radians. And once again, two non-zero vectors, A and B, are orthogonal or perpendicular if the angle between them is pi over 2. Now, if you go back to this representation, this equation, remember, if theta is pi over 2, cosine pi over 2 is equal to 0. So if I have, for example, 0 equals A dot B, or magnitude of A times magnitude of B, the only way that this is going to work out is if this top is equal to 0. So A dot B would have to be equal to 0. And so this is a quick way that we can figure out whether or not two non-zero vectors are perpendicular, is take a look at their dot product and see if it's 0. And that leads us to the next theorem. And so two vectors A and B are orthogonal. If and only if dot product of A and B is equal to 0. So in the next example, we're going to show that the vector 2i, but let's call it A equals 2i plus 2j minus k. It's perpendicular to B, which has a representation of 5i minus 4j plus 2j. Alright, so show that these two are perpendicular. Well, to show they're perpendicular, we'll take a look at the dot product. So we'll consider A dot B. In a component form, we have A is represented this way, as components 2, 2, and negative 1. And B has components 5, negative 4, and 2. Well, if we go through and take the dot product, we'll have a 2 times 5 plus 2 times negative 4 plus negative 1 times 2. Well, this is going to give us, well, 2 times 5 is 10, plus 2 times negative 4, that's actually minus 8, plus negative 1 times 2 is minus 2. And so 10 minus 8 minus 2 gives you 0, which means that according to previous theorem, these vectors are orthogonal, and they're non-zero vectors, so they're hitting each other at 90 degrees, or at pi over 2 radians. Alright, so next we'll be taking a look at direction angles. And direction cosines. We'll start with the definition of direction angles. So the direction angles of a non-zero vector A are the angles, which we're going to call alpha, beta, and gamma. And these are going to be in the interval closed interval from 0 to pi. So, once again, direction angles of a non-zero vector A are the angles alpha, beta, and gamma that A makes with the positive x, y, and z axes respectively. So let's take a look at a diagram. And let's suppose that we have some sort of vector A. And maybe that vector A looks something like this. Well, this vector A makes an angle with a positive x-axis. And that is our angle alpha. It makes an angle with a positive y-axis. And that's going to be our angle beta. And it also makes an angle positive z-axis. And that's going to be our angle gamma. Now the cosines of these direction angles are called the direction cosines of A. All right, so if we think about the vector A, for example, let's suppose that vector A has components A1, A2, and A3. And of course we're interested in the angle that A makes with the positive x-axis, the angle it makes with the positive y-axis, and the angle it makes with the positive z-axis. But if we're going to try to come up with what the angle actually is, if we want a little bit more information about, let's say, angle alpha, then let's think about the fact that finding the angle between the vector A and the positive x-axis is going to be the same as finding the angle between the vector A and the vector I. Because remember, the vector I is a unit vector that points in the direction of the positive x-axis. And so with that in mind, we know that the cosine of alpha is equal to A dot I over the magnitude of A times the magnitude of I. But if you think about this a little bit more carefully, keep in mind that I is a unit vector, so the magnitude of I is just 1. Also, if you look at the dot product of A and I, components of A are A1, A2, and A3. The components of I are 1, 0, and 0. And so this means that the cosine of alpha, when you take the dot product along the top, A1 times 1 gives you A1. You add A2 times 0, but that's just 0. You add A3 times 0, well that's also just 0. Which means the dot product of A and I is just A1, the first component of A. And as I mentioned before, the magnitude of I is just 1, so the bottom part is just going to be the magnitude of A. So cosine of alpha is A1 over magnitude of A. Now, in a similar fashion, we can figure out what's going on with the cosine of beta and the cosine of gamma. Now remember, beta is the angle that the vector A makes with the positive y-axis. But remember, J is a unit vector that points in the direction of the positive y-axis. So beta is actually also the angle between A and J. So we can say the cosine of beta is A dot J over magnitude of A times magnitude of J. But just like I, J is also a unit vector, so its magnitude is 1. So again, we're going to have the magnitude of A as our denominator. And A dot J, well, remember J has components 0, 1, and 0. So this means that the cosine of beta can be written as, well, A1 times 0 gives you 0. A2 times 1 gives you A2. And A3 times 0 gives you 0. So cosine of beta is going to be A2 over magnitude of A. And in a similar fashion, cosine of gamma is A3 over magnitude of A. Alright, so let's take a look at an example where we find the direction angles of a given vector. So this vector A has components 1, 2, and 3. Now let's keep in mind that cosine alpha, cosine beta, and cosine gamma all look very similar. It just depends on which of the 3 components you have in the numerator. Denominator has magnitude of A. So we need to figure out the magnitude of A here. It'll be the square root of 1 squared plus 2 squared plus 3 squared. But that gives you the square root of 1 plus 4 plus 9. Which means that the magnitude of A is the square root of 14. Now, from this, we know that the cosine of alpha, remember cosine of alpha is A1 over magnitude of A. Well, A1 is 1 in this case. So we got 1 over the square root of 14. So that means that alpha is the inverse cosine of 1 over root 14. And if you put that in the calculator, you get approximately 74 degrees for alpha. Now for beta, we know that cosine of beta is equal to A2 over magnitude of A, but A2 is 2. So cosine beta is 2 over the square root of 14. That means beta is the inverse cosine of 2 over the square root of 14. And once again, you get an approximation, and that means beta is approximately 58 degrees. And the last angle is gamma, and we know the cosine of gamma is A3 over magnitude of A. But A3 is equal to 3. So cosine gamma is 3 over square root of 14. So that means gamma is inverse cosine of 3 over square root of 14. Again, we approximate that and we get about 37 degrees. So here we have our approximations for the direction angles of this vector A. All right. All right, so next we'll take a look at projections. Let's suppose we have a couple of vectors. And we have a vector PQ, maybe a vector PR. Now this PQ vector I'm also going to refer to as the vector A, and the PR vector we'll refer to as the vector B. And what I'm interested in figuring out is what is the projection of the vector B onto the vector A. You might ask, well, what is that? What is the projection of B onto A? And the way I like to think about it is imagine that you have some sort of light source that's shining perpendicular to the line containing the vector A. And we want to take a look at the shadow that the vector B casts on that line. So one way to think of this is you can draw a perpendicular from the point R down to the line that contains the vector A. And this vector that goes from P to this point where the perpendicular hits the line containing the vector A, well, that is your projection of B onto A. So I guess we could take a look at this point here. We can call it S. But yeah, this vector here is what we refer to as the projection of B onto A. Now, this projection vector will either point in the same direction as A, or it will point in the opposite direction as A, assuming that, of course, the projection vector is not a zero vector. So let's think about what happened in a different situation. So let's say we have, once again, a vector PQ. But this time, let's suppose that the angle between these two vectors is greater than 90 degrees. We'll still refer to the vector PQ as A and the vector PR as B. And we're still interested in this idea, once again, of shining a light source that's perpendicular to the line containing the vector A. We want to see what sort of shadow this vector B casts on that line. And we could say that the point where the perpendicular hits the line containing vector A is going to be the point S again. And this vector PS will then be the projection of B onto A. Now this time, that projection vector points in the opposite direction as the vector A, but that's okay. So once again, we have the projection of B onto A. Now, ordering definitely matters. So if we take a look at projection of B onto A and somebody else considers it's the projection of A onto B, well, we're looking at two completely different vectors, especially in a case like this, because if I take a look at the projection of A onto B, then that projection vector is either going to point in the same direction as B or an opposite direction as B. Really just depends on the angle between the vectors A and B as to how it plays out. But if you were to take a look at the projection of A onto B, you'd have a vector that goes along here and probably ends up maybe around terminal point somewhere around there. So projection of A onto B would certainly be a different vector than the projection of B onto A. Alright, so in both cases the way this is set up, the vector PS is the vector projection of B onto A. We already have some familiarity with that notation. Now, we also have something called the scalar projection of B onto A. And the scalar projection of B onto A is the sign magnitude of the vector projection. Now, the signed magnitude of the vector projection. Well, in a case like this, we would be referring to the scalar projection of B onto A as whatever the magnitude of this projection vector is. But in a case like this, when the projection vector points in the opposite direction as the vector A, then scalar projection would actually be negative the magnitude of this projection vector. Now, if you're wondering what that magnitude is, or more specifically what the sign magnitude is, it's going to be magnitude of B times the cosine of theta. And so you may think about, well, what's theta? Well, theta is the angle between A and B. So if you go back to these diagrams here, theta is the angle between A and B, and once again, theta is the angle between A and B. Now, here you have an acute angle, so you don't have to worry about cosine theta being negative, but here cosine theta certainly is negative. Now, as far as the magnitude of the projection vector goes in this top diagram, let's just keep in mind that the cosine of theta is going to be the magnitude of that vector over the magnitude of B. So cosine theta, magnitude of the projection B onto A over magnitude of B. And so if we take a look at the magnitude of the projection of B onto A, we can get that simply by multiplying both sides of this equation by magnitude of B. So we would have magnitude of the projection A onto B is equal to magnitude B cosine theta, which is exactly what we're seeing here. Now, if we take a look at the magnitude of the projection of B onto A here, well, if we're just looking at the magnitude of the magnitude of the vector is going to be positive in this particular situation. But the sign magnitude would be negative because this projection vector is pointing in the opposite direction of A. And so if you think about what the magnitude of B times cosine theta would look like in this case, well, cosine theta is going to be negative. But if I were to take a look at this length here, then yeah, this length would be basically the absolute value of cosine theta times the magnitude of b. So it actually turns out that in this case, this magnitude of b times cosine theta is going to be negative the magnitude of the projection of b onto a. But you're looking at a sign magnitude anyway, and once again, that sign's going to be positive if the projection vector and a are pointing in the same direction, and negative if they're pointing in opposite directions. Now, this scalar projection is denoted by this notation here. So instead of PROJ, we have COMP. Right. Okay, so what about formulas? Alright, so scalar projection of B onto A. We already know this formula here. We have the magnitude of B times cosine theta. But if you think about what the cosine of theta is, remember theta is the angle between A and B. So you could think of this cosine theta as A dot B over magnitude of A times magnitude of B from the formula from earlier in this video. But the magnitude of B here and the magnitude of B here will reduce out, which means you're going to have A dot B over magnitude of A as the scalar projection of B onto A. And again, this gives us the signed magnitude of the vector projection of B onto A. Okay, so let's think about a formula for the vector projection then. Well, you already know what the sign magnitude is. That's given by the scalar projection of B onto A. And so if I want to know what a representation is for the projection of B onto A, I need a magnitude and a direction. Well, I've got a sign magnitude, and a unit vector in the direction of A will give us the direction we want. Or it'll give us opposite the direction we want, but who cares, because scalar projection is going to take that into account anyway. Well, if you think about what the vector projection of B onto A is then you want the signed magnitude of the projection vector times a unit vector in the direction of A. Alright, so the projection of B onto A, once again, you've got the sign magnitude here. And then we'll multiply that by a unit vector in the direction of A. Well, unit vector in the direction of A is 1 over magnitude of A times A. And see, one of the things to consider here is that this scalar projection of b onto a is going to be positive if a dot b is positive. If a dot b is positive, then the cosine of the angle between a and b is going to be acute. Now, if we have this is negative, then a dot b has got to be negative, which means the angle is going to be between 90 and 180 degrees. So you'd want the projection vector to be pointing in the opposite direction as a. But it's all taken care of by this part. Pointing in the same direction or pointing in the opposite direction, all really taken care of by the dot product of a and b. Put all this together. And you got the projection b onto a. It's going to be a dot b over the square of the magnitude of a times the vector a. So that, once again, is projection of b onto a. All right, so let's take a look at an example. So in this case, we'll find the scalar projection and the vector projection. The vector b, which has components 1, 1, and 2. Onto the vector a, which has components negative 2, 3, and 1. And so one thing to keep in mind is that if you're looking at the projection of b onto a, if the dot product of a and b is positive, then the projection vector is going to point in the same direction as a. And if the dot product of a and b is negative, then the projection vector is going to point in the opposite direction as a. All right, so we'll look at the scalar projection of b onto a first. And in order to do that, we need to know something about the dot product of a and b. So we have the vector with components negative 2, 3, and 1, dotted with the vector with components 1, 1, and 2. So a dot b will have a negative 2 times 1, plus 3 times 1, plus 1 times 2. Well, we get a negative 2 plus 3 plus 2, and we notice that the negative 2 and the positive 2 cancel out, so the dot product of a and b is 3. So this tells us that the projection vector, projection of b onto a, is going to point in the same direction as a. All right. Now, we also need to know something about the magnitude of a. But the magnitude of a is the square root of the sum of the squares of the components of a. And so we'll have the magnitude of a is the square root of the square of negative 2 plus 3 squared plus 1 squared. Now, square your negative 2, you get 4. Square your 3, you get 9. Square your 1, you get 1. And so we take a look at that result, 4 plus 9, 13 plus 1 gives us 14. So the magnitude of A is the square root of 14. All right. So now we take a look. We have the scalar projection of B onto A. Same thing as A dot B. By magnitude of A. Now your A dot B is 3. Magnitude of A is the square root of 14. So that means that our scalar projection of B onto A is 3 over the square root of 14. So that's the magnitude of our projection vector. Now you take the magnitude of that projection vector times the unit vector in the direction of A, and that's going to give us our vector projection of B onto A. Of course, that's all encapsulated in the formula that we have here. Now, fortunately for us, we've already figured out what A dot B is. But we also know what the square of the magnitude of A is, because it's the square of the square root of 14. So the projection of B onto A is 3/14 times the vector A and the vector A has components -2, 3, and 1. And this means that the projection of B onto A can be written in this form. So you take your 3/14 times -2, gives you a -6/14, or -3/7. 3/14 times 3 gives you a 9/14. And then 3/14 times 1 gives you 3/14. Alright, so that's our projection of B onto A. Alright, so there is one last part to this section. And so here we have work done by a constant force, F, and moving an object through a distance d. Is given by work equals force times distance. But it only applies if the force is directed along the line of motion of the object. So let's suppose that you have a constant force vector that's pointing in some other direction. So let's take a look at a diagram we can use to illustrate this. So we have our force vector, which is the vector PR, and certainly is not pointing in the same direction that the object is moving. But if the force moves the object from P to Q, then we have a displacement vector D, which is this PQ. Now the work done by this force is the product of the component of the force along D and the distance moved. So once again, the work that's done by the force is the product of the component of the force along D and the distance moved, which is going to be the magnitude of D. Now, what does that really mean, though? Well, what it means is that we're interested in projection of F onto PQ. So let's take a look at this vector here. Now once again, this vector is projection of F onto PQ. Now we could also say it's the projection of F onto D, because D is equal to PQ as illustrated here. So really what we're saying here is that we're interested in figuring out this magnitude, but that magnitude is going to be equal to well, remember the scalar projection of F onto D. Scalar projection of F onto D is going to be F dot D over magnitude of D. So you take the product of the component of the force along D and the distance moved. Well, that means that work is going to be this times distance moved. Well, distance moved is the magnitude of D. Now you may notice that magnitude of d here, magnitude of d here will reduce out, which means you get W is equal to F dot D. Now, of course, another way to look at this is that W is equal to magnitude of F times magnitude of D times the cosine of the angle between those two vectors, which we're going to call theta. Because once again, there's your F, and then this vector PQ, once again, is the vector D. All right, so let's consider a couple of examples. So in this first example, we have a wagon that's pulled a distance of 100 meters along a horizontal path. By a constant force. And that force is going to be 70 Newton force. Now the handle of the wagon is held at an angle of 35 degrees. Again, handle the angle, or the handle of the wagon is held at an angle of 35 degrees above the horizontal. So let's find the work done by the force. Now, when we take a look at examples like this, sometimes it might be helpful to have the W as the dot product of force and distance, and in other cases it might be more helpful to have that W as the magnitude of F times magnitude of D times cosine theta. Now, for this example, it's definitely this formula is going to be a bit more helpful, because we know the magnitude of the force vector, 70 newtons. We know the magnitude of the displacement vector, 100 meters. We also know theta is 35 degrees. So we write down that relevant information. And we know that W is magnitude of F times magnitude of D times cosine of the angle between those. So now it's just a matter of multiplying together the 70, the 100, and the cosine of 35 degrees. For your cosine of 35 degrees, you're going to want some sort of approximation, but you take 70 times 100, and that's going to give you 7,000. You take 7,000 times cosine 35 degrees, and you'll get, that's approximately 5,734. Units, Newton meters, or joules. So you can write it either way. All right. So let's take a look at one last example. And in this example, we have a force is given by a vector. And that vector is F equals 3I plus 4J plus 5K. And this force is going to move a particle from the point P with coordinates 2, 1, and 0 to the point Q. And that has coordinates 4, 6, and 2. So we're going to find the work done. So we're given the force vector here, and we're also told that the force moves a particle from the point P to Q. Now this vector PQ is going to be our displacement vector. And if you want to get this displacement vector, this vector PQ, then you need to take terminal point coordinates minus initial point coordinates. Terminal point is Q, initial point is P. So the first component of PQ will be 4 minus 2. Second component will be 6 minus 1. And the third component will be 2 minus 0. Now this means that this displacement vector D has components 2, 5, and 2. But we also know that F has components 3, 4, and 5. And on top of that, we know that the work done, which is what we're trying to figure out in the first place, is the dot product of F and D. So the components of F, 3, 4, and 5. Components of D, 2, 5, and 2. And so to get the work done, we'll take the dot product of F and D. We'll have 3 times 2 plus 4 times 5 plus 5 times 2. And that gives us, well, 3 times 2 is 6, 4 times 5 is 20, 5 times 2 is 10. Add it all together, and you get W is 36. No units are given, so this is as good as it gets here. And with that, section 12.3 is finished. So let's take a look at some recommended exercises here. So 3, 5, 7, 9, 15, 17, 23, 29, 33, 39, 41. $49, $51, and $55.